Okay, so now we have a very cool new player on the scene. This we're going to cover in chapter, let's see, chapter 21 and 22. Klein talks about it here as if it's review, but we're going to be seeing it for the first time here instead of the first time there. So this is called Gilman Reagent, and it's a lithium dialkyl, right? Lithium dialkyl, so we got two R groups in there. 1, 2, dialkyl cuprate. All right. So the way we're going to do that is we're going to take an organohalide, which is really, you know what that is, right? That's a R, let's say Br. Treat this with lithium, and we're going to get RLi. So we'll make a lithium or an organolithium reagent first, right? And then we treat it with copper, let's say bromide, and we're going to make this. Well, you see it here, right? That's what we're going to make. So this is called a Gilman reagent, and it's different in a couple ways than organolithium and organomagnesium. So these are big words, and I stumble over them. Organolithium, organomagnesium, and then very different are this lithium dialkyl, whatever. Okay, so we're going to say Gilman. All right, these act very much the same, like this. And this one, for reasons described in 28.1, is much less ionic. Right, so you really can't treat this. I honestly think it's going to be useful to think about it like that. But we have to remember it differs in a couple ways. Different. How do you spell different? Different, okay? And let's see, I think 3 ways. 1, 2, and 3. And you could get this, you don't need me to tell you what they are, but I'm going to point them out here since we're talking about it. All right. So first of all, the way that these are just examples. We just did this in the previous slide, right? So we took some on the previous slide. Where's my pen here? Rx, which in this case is butyl iodide, right? BUI, which is what we got here. And we, through 2 different steps, made this a dialkyl cuprate, right? A lithium dialkyl cuprate, which I'm simply going to call a Gilman reagent. Somebody, one of my colleagues, calls this coulis, right? Can you see why she calls it coulis? I don't know. I'm not going to call it coulis, I don't think, but anyway, it might help you remember what it is if you do that, okay? So it's coulis. Now, here's another, not really alkyl, but aryl, right? Lithium diaryl cuprate, right? Here's a vinyl, lithium divinyl cuprate, right? Okay, so the same. We had exactly these ways of making things for the magnesium and the lithium. So let's move on. Let's see how they're different now. So we're going to find out in chapter chapter 21. Here's something we can do. If you have a chloride on here, we can do that. NaCl chloride. We haven't done it yet, but we'll see it in chapter 21. And in chapter 22, this is one thing that you need to know right now. So if you had, normally if you would have a nucleophile, you would expect it to go here, right? And if you have a lithium or magnesium, that's exactly what it's going to do. But Gilman does not do that. Really? Okay. Very cool. We'll do this in chapter 22. You don't need to know it now. I don't think. Let's look at our problems. Pretty sure we're not going to be doing that right now in our problems. But it's selective, all right? And the reason is because it's not a classic anion. All right, so the Gilman reagent can also react with alkyl halides. So after you have This one, I don't think you've seen this yet with your other one. Yeah, you did. Yeah, you saw this with Grignard. But Gilman can do this too, right? So what you have here, thinking about it like this, boom, boom, there we go, right? So this is called a Corey Posner Whitesides-House reaction. I don't think I'm going to say that unless I'm actually looking at it. I don't think about it like that. I just think about it as an SN2 reaction. Okay, such reactions are performed at low temperatures with diethyl ether, or THF, the molecular formula of which is THF. Okay, two different solvents. This one is polar aprotic. This is non-polar, right? Look those up and remind yourself about those. And so here's some examples then of these reactions. Getting ready to do something that's kind of cool. So I've only talked about the first difference, and that is that it's more selective. We're about to see a big difference here that's pretty cool. So this is exactly what you would expect, except, okay, here's something you got to watch out for now. Only one of these comes over here, right? So here's my, I don't know, a pentyl group, right? So it's going to become R pentyl. 1, 2, 3, 4, 5. See that? One of my R's comes over with this phenyl, so it becomes R phenyl, or R benzene, right? One of the R's comes over to this vinyl group, and it becomes R vinyl. Okay, now tertiary and secondary alkyl halides don't favor the desired substitution product, and I want you to think about why that might be. Do think about that. Why would that be? Okay, so this is cool. This is very cool. The stereospecific now. The Corey Posner Whitesides-House reaction is stereospecific for reactions involving alkenes. This is something we've never been able to do before. And that is, you see you have an E. Where's my pen? Where's my pen? Here it is. You have an E alkene here, right? Here's another E alkene, right? Because we made it. That's, of course, that's the way we made it, right? Well, it's always going to be two of the same thing. And here we have a Z. Can you see that? And when you put the E on there, it's going to come in as an E. Really? Wow, that's bizarre. So practice with this reaction. Make something with it. Make yourself a synthesis problem with that reaction. You've never been able to do that before, and there it is. So we did one other stereospecific reaction with alkenes before, and I wonder if you can remember what that was. What was the other stereospecific? What was the other stereo reaction that we did before? Okay, now the mechanism is not well understood, and so we are not going to try to understand it. All right. Is that the last slide? No. Okay. Because the Gilman reagent is somewhat selective, the Corey, yeah, we already said this now. Because the Gilman reagent is somewhat selective, this reaction, which I'm going to call Gilman, it's really a Gilman reagent, right? There's a Gilman reagent. Here's the Corey Posner Whitesides-House reaction, which I'm never going to say unless I'm looking at it, is selective. That means this is not going to go here, right? We said that before. Now, Grignard will go there. The Gilman will not. The Gilman's going to come over here and go right on top of that vinyl, in the vinyl position. Look at that. All right, and I think that's the last. No, we've got one more. All right, so complete the retrosynthesis below using the Corey Posner Whitesides-House reaction. Okay, give two possible methods. I'm actually not going to explain this to you. I want you to do this synthesis problem as practice. All right, good luck.